In this video here, we're going to take a look at modeling with numerical methods. So for this video then, all we're going to do here is look at how we can use numerical methods to model real life situations such as the following here. So what do we have then? So for example, we could model the price of a vehicle, or we could model the height of a bouncing ball. And then finally here, we could model the height of a roller coaster during a period of the ride. So these three examples here that I've chosen, nothing special about any of these examples. I have just chosen them at random. But it's just to give you a bit of a snapshot and a bit of a, example as to the type of things that we can model using numerical methods. So let's get started then with the first of our numerical methods here, and that is iteration. So the question is based around iteration. We will always be given the iterative formula within the question. However, you may have to occasionally show how the iterative formula is derived. Now, we have seen examples of this before, right? Go back and check our video on iteration if you want to see an example of this here. Obviously, it's not applied to any real life situation or context because we wasn't looking at modeling. That's what we're looking at in this video here. Okay, so we'll cover that in a little bit more detail as we work through an example later on. So moving on then, we now have the second of our numerical methods here, and this is for the Newton-Raphson method. So if the question uses the Newton-Raphson method here, then we're going to use the following result. So this result here, hopefully you are familiar with this result. This is the Newton-Raphson method. So if I'm showing you something here that you've never seen before, right, this looks completely new, just go back and watch our video on the Newton-Raphson method where we do cover this in a little bit more detail. Okay, so nice and straightforward for the Newton-Raphson method. This result is also given in the formula book, so not something that you do need to worry about. Okay. And then finally here, we have the very last numerical method here, and that is the trapezium rule. So if the question involves the trapezium rule, then we're going to use the following result here. So this result then, this here is the trapezium rule. And again, similar to the Newton-Raphson method, right, or exactly like the Newton-Raphson method, this result here is also given in the formula book. So again, not something that you do need to worry about memorizing. So there we have it, a very quick introduction here to modeling with numerical methods. But as always with these modeling videos here within A-level maths, we're not introducing any new material. We are just largely recapping the chapter as a whole. So we're just recapping numerical methods here. And what we're going to do now is apply this to a real life situation or context. Okay. So all we're going to do then is just take a look at one example. So let's get started then with this question. So let's have a look then at this one practice question here for modeling with numerical methods. So for this question here, as we can see, right, a ball is thrown upwards where the vertical height of the ball is modeled by the given function here. We're told that the diagram above shows a sketch of part of the curve, and we're also told that the curve has a maximum turning point at Q here, as we can see on the diagram. So as you can see, right, the context here is pretty dull and boring. It's never particularly exciting. But for the first part of this question here, part A then, so for part A then, it asks us to find h prime of x. That's the derivative of h of x here with respect to x. Now, looking at this function here, right, nothing particularly challenging, but what I can see is for this part here, we will require the use of the product rule. Okay. I need u and v here. So obviously for the product rule, it doesn't matter which one you define as u and which one you define as v, either's fine. So working from left to right here, I'll define u as minus 0.1x here. Minus 0.1x, like so. We also need u prime as well. So u prime is the derivative of u with respect to x here. So nice and straightforward. That gives us minus 0.1 here. Okay. And now doing the same here for v then. And we also need v prime. So for v here, that will be e to the x. So we get e to the x there. And again, the derivative of v here with respect to x, nice and straightforward. Again, we just get e to the x here. Okay. So now let's find h prime of x here. So that's the derivative of h of x with respect to x. So h prime of x here. So starting off then, 4x will just differentiate to give us over there, like so. And we now need to use the product rule here on this product of functions, right? So in that case then, I get u times v prime. So I get minus 0.1x e to the x, like so. And I also get minus 0.1 times e to the x. So I also do u prime times v here. And we add those together. But obviously, if this is negative, it'll just be subtracted. So I get minus 0.1 e to the x there. Okay. Now, sometimes you might be asked to give it in a specific form. It doesn't ask for anything specific here for part A. So I'm just going to leave my solution as it is here. Okay, so that gives us the solution to part A there. So now moving on to part B here. So for part B then, it says hence of y show that the x coordinate of Q is a solution here to the following. So x is equal to ln of 4 over 0.1x plus 0.1. So for the x coordinate here of Q, okay, so for Q then, if this is the maximum turning point, what we know is the first derivative here, h prime of x, will be equal to 0. Okay. So we need h prime of x is equal to 0. Okay. So in that case then, let's set this here equal to 0. So therefore 4 minus 0.1 x e to the x minus 0.1 e to the x here is equal to 0. Okay. So what I'm going to do now is take these two negative terms here over to the other side to make them positive. And in doing so, then what I get here is 0.1x e to the x plus 0.1 e to the x is equal to 4 here. Okay. And what I want to do now is factor out the e to the x here, right? So you can kind of see where you need to go from here. I need 0.1x plus 0.1 for my denominator. So if I factor out e to the x here, what I get then is e to the x 0.1x, 0.1x there, plus 0.1. Okay. And hopefully now you can start to see how this will shape up. So that's equal to 4 then. So now I'm going to divide by 0.1x plus 0.1. So e to the x is equal to 4 all over 0.1x plus 0.1, like so. And then finally here, if we just want x here, obviously I need to take logs here, the natural log of both sides. And in that case then, x is equal to ln. So x is equal to ln of 4 over 0.1x plus 0.1 exactly as we require, right? Just taking logs of both sides here, then we get exactly as we require. So 4 over 0.1x plus 0.1 there. Okay, so as required. And there we have it. So that gives us the solution to part B. So as required there, giving us a solution to part B. And now we arrive at the very last part of this question here. So as we can see, right, this question here is based on iteration, right? So it's not the Newton-Raphson method, it's not the trapezium rule. We're going to use iteration. And what we're given here is the iterative formula. Okay, so we've actually derived the iterative formula here in part B. And now for part C, we need to use it. Okay, so there's two ways to do this. You can do it by hand, do it manually, or you can use your calculator. Now, I would definitely recommend using method 2 here, using your calculator, rather than doing it by hand. Either method's fine, but obviously doing it by hand is going to take, a considerable amount of time, whereas by doing it by calculator, it's much quicker. Okay. So what I'll do here is I'll demonstrate how you do it by hand, just in case you're not familiar with this method here of iteration. And then I'll show you how to do it on your calculator. So for part C, we don't have a lot of room here, but I should be able to kind of briefly show you how to do this. It wants us to use this iterative formula here, right? So x of n plus 1 is equal to ln 4 over 0.1 xn plus 0.1. Now we're told that x naught is equal to 2.3 here. So let me just make a note of that here. So x naught is 2.3. And we want to find values for x1, x2, x3, and x4, given our answers to 3 decimal places. So what I need to do here is use this iterative formula. So for example here, we want x1 here, right? We're given x0, we want x1. So for x1 here, that's going to be ln of 4. It's ln of 4 all over 0.1. So n here must be 0, right? So to get x1, n must be 0. So I get 0.1 x0, 0.1 x0 plus 0.1. Okay. And we know that x0 here is 2.3. So what I get here then is ln of 4. As you can see here, room is getting a little bit tight. I'll try my best to fit it in. So 0.1 times 2.3 plus 0.1. Okay. Now, all I need to do then is just put this here into my calculator, right? Obviously, I can't do this off the top of my head. It would be impressive if I could, but I can't. So using my calculator, what I get here then is 2.495 to 3 decimal places, right? So 2.495 here to 3 decimal places. So that would be x1. But now I'd need to repeat this here for x2, x3, and x4. And you can start to see now why this might take quite a bit of time doing it by hand. So let's have a look then at how we can answer part C by using our calculator. So if we do part C up here then, just so we have a bit more room here. And as we've already mentioned, right, we do want to use our calculator. So we've demonstrated partially here how we can do this by hand, but as we've already noted, it is quite slow and it is quite tedious. So by using our calculator, we can speed this process up by quite a bit. So let me just grab my calculator here so we can walk through this together. So the first thing that I need to do here then is input 2.3 into my calculator here. So I type 2.3 and then press enter or execute, whatever your kind of input function is for your calculator. So 2.3, I press enter then. And what this does here is it stores this 2.3 into the memory of our calculator. Okay. Now, if I use the answer button or the answer function here on my calculator, it will recall this value here. And that's quite useful because we can use this now to find the values of x1, x2, x3, and x4. So wherever there's an xn here, we use the answer button or the answer function on our calculator. So now we need to use this iterative formula here to find the values of x1, x2, x3, and x4. So if we do the following here, we will get this. So I get ln of 4. So all I'm doing here, right, is just using this iterative formula now, just replacing xn with the answer button or the answer function. So I get 4 all over then 0.1 answer. Again, just replacing xn with the answer button or the answer function on your calculator plus 0.1. Okay. So now we'll replace answer here with the value that we've just inputted, this 2.3. If I quickly enter this into my calculator here, right, do take care as you enter this into your calculator. Obviously, the danger here is that you make a tiny mistake within this working here and putting this into your calculator. And obviously, if you do make a tiny mistake, then the values of x1, x2, x3, and x4 will all be incorrect, right? So obviously, we're not going to get any method marks here. So we won't get any method marks. Obviously, we do use our calculator like this. We do need to be careful. So inputting this here using our calculator, so I get ln of 4, and I will use brackets here just so I can be extra careful. I get 0.1 answer plus 0.1 here, close my brackets. And if we do this correctly then, as you would expect, we do get quite a few decimal places here, right? So hopefully, if you've done this correctly here, what you should get then is 2.494956986. Now, the question does want us to give the answer to 3 decimal places, and we've already done that here for x1, right? So here then, let's just note that x1, if we round this to 3 decimal places, then gives us the exact same answer, right? Which is what we would expect. If we get something different, then we know that something has gone wrong. Okay, so we get 2.495 there to 3 decimal places. And the magic here then is that if I now press enter or execute, whatever your kind of input function here is, then it will now give me x2. So what it's going to do now is replace 2.3 here as my answer and replace it with 2.495 here. Or, well, it'll keep the full kind of decimal equivalent, but it will basically use this value now to find x2. Okay. So in that case then, x2 here, if we press enter. So hopefully what you'll see now on your calculator display here is 2.437558386. And again, just running this to 3 decimal places here, what we get then is 2.438 here. Okay. We also need x3 and x4 here, so let's continue. So x3. Again, just press enter or execute. And hopefully what you can see here is we get 2.454118006. And again, just running this to 3 decimal places, then I get 2.454. And then finally here for x4, what I'm going to get here then, again, just press enter one more time. Running this to 3 decimal places, then we get 2.449. Okay. And there we have it. Now, if we was to continue pressing enter here, you used to press this a load of times, right? You should hopefully see that this converges. And what I get here then, once this converges, I get 2.450391,695. Okay. So that's how we can kind of approximate a root here by using an iterative formula and our calculator. But we do only need x1 to x4, right? But there we have it. And as you can see then, by using our calculator here, it is a much quicker process rather than doing it by hand. Definitely a lot more tedious, so a calculator method is preferred, but you don't have to. You could just do it by hand if you do prefer to do that. And either's absolutely fine. Okay. But there we have it. So that gives us the solution to part A here. This was the solution to part B. And this here then was the solution to part C. And there we have it. So that gives us the solution to this practice question here. And that brings the end then of this video here on modeling with numerical methods.